All right, guys, so I'm going to break this up into little videos so you can take it in pieces. This is going to be the first one. Again, I'm just going to move through the notes that I have, the slides that I have, and give you most of what you would have gotten in a lecture. The only difference is going to be that you can stop it and replay it and move away from it and come back to it as you need over the next couple days. Again, when we get back to class on Tuesday and Wednesday, depending on what section you're in, we'll do a little bit of practice, but I will take the opportunity to go ahead and move on to other material. So we're going to have two primary types of compounds that we are going to name. We are not going to do much with organic nomenclature. That will be for your organic classes, and we'll let Drs. Nichols and Castleman tackle that. So what we're going to have in this class are either ionic or molecular compounds, and it's going to be your job to tell which one is which, because there are differences in the naming rules. So we have ionic compounds. Those are going to be composed of a metal and a nonmetal, and those kinds of compounds will have the properties that you see there. We can hit them with a hammer and they'll be malleable. They won't necessarily break. If we melt them, they will conduct electricity. If we dissolve them, they'll still conduct electricity. Those are things inherent to ionic compounds. In terms of nomenclature, you're going to need to look for a metal and a nonmetal, and that way you will know that you are using the ionic nomenclature rules we'll see in a little bit. Remember when we talked about the periodic table, we pointed out the stair step, and that those compounds to the right and above the stair step were nonmetals. Those compounds to the left and below the stair step are considered metals, all the way to the very left of the periodic table. So that's how you'll know what you have. Molecular compounds, on the other hand, are going to be composed solely of things to the right and above, or solely nonmetals. So that is what you're going to look for. Whether everything's together in that top right-hand corner of the periodic table, or whether your two or more things, are spread out across the periodic table. Now, how our atoms come together to form bonds dictates whether it's an ionic or a covalent compound, and we'll talk more about this. We'll talk about what leads to the bonds. Once things are bonded, we'll talk about geometries. But for now, we're just worried about covalent and knowing that it is a bond between non-metal compounds where the electrons are shared. They may not be shared evenly. There may be a polarity to them, like in that case or in that case there, right? Your HBr and your HF both are to the right and above the stair step, so they're both non-metals. So the electrons, which will be found between, or they're not actually found between, but here we expect you to know that that line denotes the electrons. Okay, they're shared. Sometimes they're shared evenly in this case, and so you would have the same probability of finding an electron around either of the fluorines in that bond. In the case of HBr and HF, they're shared unevenly, and we have more of a chance of finding them around the Br or the F than the H, but they're still shared. Now we'll talk about polarity later, and we'll talk about that uneven sharing. But because these are both nonmetals and these are both nonmetals, those guys are going to make covalent compounds, and we'll have to use molecular naming rules when we name those. Over here, we have a metal and a nonmetal. So sodium can be found all the way to the left of the periodic table. Fluorine is above and to the right of that stair step. So this would actually form an ionic compound. And there's not really a bond. Notice that there's no line here. It's just an empty space. There's a transfer of electrons from the positively charged cation to the negatively charged anion. So no actual bond, just a sharing of electrons and electrostatic attraction that keeps those guys together. They're together in a matrix, and so when they get packed together at the corners of that of the matrices, they stay pretty well until you get something around them that would make them leave, like water. Know that these models, especially these and these, represent extreme cases where we have an absolutely perfect bond and then no bond at all, but rather a sharing, and everything probably exists somewhere in the middle. Okay. We will get to electronegativity later when we talk about electron shape. Now, here are some examples of ionic compounds and covalent compounds. Again, all of these would be found above and to the right of the periodic table, because if you look at everything listed in all 4 of these rows, those are all nonmetals. Here we have 1 metallic piece and 1 nonmetal piece. Okay. Take a note that all the nonmetals are second, all the metals are first. We will talk about that more later, but that's the pattern we're going to follow for all of these ionic compounds. Essentially, just think of moving left to right on the periodic table. All right, so these questions are present in your notes. Does the classification seem to be made based on how many atoms of each? Absolutely not, right? So here we have 5 total atoms in the copper tetrachloride there. 5 total because there's 4 chlorides. There's 1 carbon. If we go to the P2O5, there's 7 total atoms. So it doesn't matter how many atoms there are. Excuse me. What matters is where those atoms come from on the periodic table. I'm slowly dying while I'm making your video, so I hope you appreciate this. All right. There is, in fact, a trend. All nonmetals, metals and nonmetals. Now, notice there's not a third column that only has metals, right? We're not really going to name alloys in this class. Okay. And I helped you write that rule if you're going through and following the notes. All right, so covalent bonds are going to be present in molecular compounds. They are present between non-metal species. So if we go through these, this guy here has 2 nonmetals. Look up both of those elements on the periodic table. You'll see they're in the top right corner. Iron is a transition metal. Chloride is a nonmetal. This will be an ionic compound because of that. Rubidium is in a main group, but it's still a metal. And then chloride is a nonmetal. So this is ionic. Remember that they can come from the transition metals, or they can come from groups 1, 2, and sometimes 3 when we get to the aluminum, right? All right. We've talked about the language thing in chemistry, how we're going to use words differently than you may have seen. Lots of people use molecules to just describe anything that has some atoms attached to each other. And that's not necessarily the case. The molecules are all going to be neutrally charged, which is okay. But they're going to consist, if you'll look at that, of all nonmetal compounds, or atoms, sorry, nonmetal atoms. Compound, on the other hand, can have metals in it now. So here we have an ionic compound. Here with water, we have a molecular compound, still a compound. Here we have ethanol, which will be a molecular compound. These last 2, water and ethanol, contain all nonmetals. Here we have a metal and a nonmetal. So we have a compound, but not a molecule. So all molecules are compounds, but not all compounds are molecules. Think back to a square is a rectangle, but a rectangle is not a square thing that you learned in junior high. Kind of the same idea here. Molecules are going to involve molecular bonds, covalent bonds, so they have to be between non-metal species. A compound just has an interaction between atoms, whether that be an electrostatic attraction like an ionic compound, or whether that be a sharing of electrons like you have in molecular bonds or molecules. All right, when we look at chemical formulas, everything we need to know about a formula is here. We have the actual symbols for the elements, which should match what's on the periodic table. And then these subscripts denote the count of that element. So for water here, we have 2 hydrogens and we have 1 oxygen. For vitamin B12, it's big and chunky. And if I drew a picture, it would take me a minute. So instead of the picture, we write something simple like this, where we have lots of carbons, 63 of them, lots of hydrogens, 88 of them, 14 nitrogens, 14 oxygens, 1 random metal stuck in there, which is cobalt, and then a phosphorus. Okay, make a note, you don't have to name things like this. That is big, and it's chunky, and it's complicated. It is in here so we can teach you how to read these. The subscript that describes the element goes right behind it, okay? If there's not a subscript, like there's not for the cobalt or the phosphorus, you assume that there are 1 of each of those. Some of our elements are special. The ones that you are going to need to recognize are these diatomic elements. These are elements that don't exist just as a single atom. And there's only 7 of them, and it's easy enough to group them and learn them that way. So remember that we can move hydrogen over here technically. So there are going to be 7 of them. We've got nitrogen, oxygen, fluorine, chlorine, bromine, iodide, and hydrogen. These are your 7 diatomic molecules. You never have an H. You always have an H2. There's no H that exists in nature. It's H2 that exists in nature. You never have a single atom of oxygen. It's always O2. There's O2 in the atmosphere. Same thing with nitrogen. You never have a nitrogen floating around. It is going to be of utmost importance that you learn these 7 diatomic elements, especially when we get to balancing equations. Because if you have a word problem that says hydrogen reacts with chlorine to form hydrogen chloride, balance the equation. If you don't know that there's H2 reacting with Cl2, then you're going to balance your equation wrong. These top 7, the diatomics that I put a red box around, and these over here that I drew on the periodic table, you're going to have to memorize. Make a note that this is a great place for flashcards. You can make one flashcard where the front says Cl2 and the back says chlorine so that you just convince yourself that it's an element. You can make a flashcard that says 7 diatomic elements and you could write them off all on the back. These polyatomics that are down here are going to be less important that you memorize them. If we see phosphorus or sulfur or carbon and I expect it to be the polyatomic version of it, I will include that in the problem. So these aren't necessarily things that I want you to memorize. But you have to know these 7 diatomics. They're going to show up. They're going to show up to trick you. So you have to know that they're H2, O2, and N2. So if I ask you for the formula for nitrogen, it's not an